We are about to begin some of our geometry proof work, and 2-7 has us looking at some segment congruency and segment proofs. So before we begin anything else, we need to revisit the segment addition postulate. We have used this, you have used this, you know this, we've just never called it the segment addition postulate. So let's go ahead and I'll show you or remind you what it is. The segment addition postulate says that if, we'll say B is between A and C, then, and actually I'm going to leave this blank for a minute, and we'll see if you guys can remember what this would be. So if I have a point between two other points, remember that could just be anywhere in between, what would the equation look like for this? Well, I would say that AB plus the length of BC would equal the entire thing. And again, we've done this. Now we just need to know that that's called the segment addition postulate, so that when we see it in a proof, we're able to give reason to it. So let's look down here. Here we have a proof that we want to write. It tells us that CE is congruent to FE, and it tells us that ED is congruent to EG, and it wants us to say why CD is congruent to FG. Well, and this would make sense. If these two little parts are the same and those two big parts are the same, when you add them up, the entire lengths would be the same. And that hopefully makes a lot of sense. Now we need to go through and we need to give actual reasons why. So I'm going to do that for you. And you're going to have some other ones that look like this. I really like 2-column proofs for this work, so that's the way I'm going to do them. But right now you guys also know of the paragraph proof. If you'd like to try to write it out in a paragraph form, I can help you with that also. Okay, so the first thing you always do is you start by listing out the things that are given. So CD is congruent to FE, and ED is congruent to EG. That's given. And somehow I need to start writing this into using the segment addition postulate. So I just know that I'm going to have to say that these things are equal. So I'm going to say that the lengths of them are equal. You probably wouldn't know that right off the bat, and that's why I'm telling you. But that usually will be one of the first couple steps in these proofs, and that is the definition of that word congruency. If you want to write the definition of congruent segments, you could do that. I usually just write the definition of congruency. Okay. I had let you know before that we will be using the segment addition postulate. Before we do that, this next step is usually pretty tricky to see. So let me kind of outline it. If I have CE equal to FE, and that was given, CE is equal to FE, I want to somehow be adding on ED and EG. Could I add on ED and EG? Yes, I can do that. And the reason is maybe not what you would think. The reason for this is the addition property of equality. And the reason it's the addition property of equality is I am adding on 2 equal parts to each side of this equation. So even though I'm not adding on like 5 plus 5 to each side or 8 plus 8 to each side, I'm adding on things that I already know are equal, and that's an example of the addition property of equality. Let me go back and find my pink pen. For the next step then, I'm going to go through and I'm going to say what the segment addition postulate is for both of these two segments. So for this one here, I can say that FE plus EG is equal to FG, And also for the other segment, CE plus ED equals CD. And both of these are illustrations of the segment addition postulate. And if you want to call it step number 4 and step number 5, you can. Or if you just want to kind of put it together like this, you can do that also. Okay, this next step is also maybe a little tricky to see the first time. I'll change colors for this again. For this part here, CE plus ED, well, this is just another way of saying CE plus ED is CD. And then this portion here, FE plus EG, well, another way to say FE plus EG is FG. So I can use substitution to say that those two parts are the same. Oops, forgot my S. Substitution. And then the last step for this, the last step is I'm going to say that I'm almost done. I wanted to prove why these things were congruent. So these are congruent because now I've said that they are equal. And CD is congruent to FG. And this is an example of the definition of congruency again. Congruent things are equal, equal things are congruent. Both are examples of the definition of congruency. I'd like to revisit these real quick and just show you how we're going to see them with our segments. The reflexive property, again, remember, is something is equal or congruent to itself. So we might see that segment AB is congruent to segment AB. For the symmetric property, it might be something like if AB is congruent to XY, then segment XY is congruent to segment AB. And the transitive property might say something like if segment AB is congruent to segment ST, and someplace you know that segment ST is congruent to segment YZ. So if you had those as like 2 steps in your proof, then you could say that segment AB is congruent to segment YZ. And just another example of the reflexive, symmetric, and transitive. Transitive is going to be the one that we see the most. In this last proof, we have some information here. It says the route for a charity fitness run is shown. Checkpoints X and Z, so let's see, X and Z are the midpoints between the starting line and checkpoint Y and checkpoint Y in the finish line, respectively. So when I'm looking at this, if checkpoint Y is the same distance from X and Z, prove that the route between Z to the finish line, which is over here, is congruent from the route from the starting line to checkpoint X. And again, all of this stuff should kind of make sense. If these are equally spaced, then yes, those parts will be equally spaced also, but we need to come up with a systematic way of how to show that and how to prove that. So again, I really like the 2-column proof. We have some flexibility with how we set this up. So I'll kind of show you the way I would do it, and I think, at least for me, this is the easiest way. So for step 1, what I'm going to do is I'm just going to take the first thing that's given and write that that's given. And then what I'm going to do from that is I'm going to say what I know about it. So if X is the midpoint of SY, then that would let me know that from S to X, that's congruent to X to Y. And I'll go ahead and mark those here on my picture. At the same time, because this will be the same reason, I'm going to say that Z is the midpoint of YF, and I can say that because Z is the midpoint of YF, that YZ is congruent to ZF. And the reason for both of these is this is the definition of the word midpoint. Some places in your book it calls it the midpoint theorem. I prefer to use just the definition. You know it's the midpoint, you know these are congruent. That's just what that word midpoint means. So if that's ever the case, you just write definition. And then I'm also going to say that the other piece of information that was given, I got to kind of squeeze it in, sorry about this, that x, y is equal to yz. So we just have to remember that these two parts are equal to each other. Just to put my congruency marks in there. So what does equal mean? Equal means that they're congruent. So I would go ahead and say that next. I'd say that xy is congruent to yz, and that is the definition of congruency. Remember, congruent things are equal things are congruent. It goes either way. So now what I can do is I can use the transitive property. And I know this is probably like very hard to see, the transitive property here. So I'll go ahead and like use numbers instead of all of these different letters because that gets a little confusing. So I have this first thing congruent to the second thing, the same second thing congruent to a third thing, the same third thing congruent to a fourth thing. So I'm actually using the transitive property kind of extended version here. We can say that Sx is congruent to ZF, and whoops, this is step number 4. This is the transitive property. And then this is almost what they wanted me to say. If you just look at here, all I need to do now is just flip the order of this to say that ZF is congruent to SX, and this is symmetric. So we will work together on this in class, and hopefully I can help you out if you have questions.
Charlie bit me. Ah.